obscured starbursts and also their implications on galaxy assembly and evolution in early times. And what I mean by dust-obscured starbursts are the most prodigiously star-forming galaxies in the universe. These have individual star formation rates of 100 to 1,000 solar masses per year. So they're rather extreme specimens that are fairly rare, but also very interesting in their implications, particularly in the early universe. I want to start by just giving some context by showing you this map, which is now fairly ancient. It's 15 years old. It's the first deep field extragalactic map in the millimeter at 850 microns, centered on the Hubble Deep Field North. And a remarkable discovery from the early days of deep field millimeter data was that there are too many dusty star-forming galaxies in the early universe at high redshift. And what that means is, if we take what we know from the local universe, of our understanding of these extreme galaxies nearby, and just extrapolate that naively to the early universe, we wouldn't expect to see a single pink source in this map at all, given its size. But there are quite a few, and the implications for what that means for galaxy evolution at early times is rather spectacular. So what I mean, here I'm showing a cartoon of redshift versus the star formation rate density plots of the Lilly-Maddow plot. If we take all of our data from the optical and UV and place it on this diagram, see it looks something roughly like this, where it peaks around redshift 2. Maybe there's a plateau and then starts to decline at earlier redshifts, but that's a little ambiguous. But this is the total estimate from optical surveys. But if we look at infrared luminous surveys, what we see is that these dusty star-forming galaxies are very, very rare in the nearby universe. But as you go back to redshift 1, redshift 2, the prevalence of these systems increases over 1,000-fold and might contribute rather significantly to the total star-forming budget of the universe. This is a schematic of the background radiation. The large peak off to the right here is the cosmic microwave background. But there are also these two other humps, one in the optical and UV here, and another in the far infrared submillimeter. And over the years, we've gotten to know quite a bit about the optical background. We're able to resolve it into individual sources thanks to large surveys like the Sloan Digital Sky Survey, and the Hubble Space Telescope has been really fundamental in driving this science for several decades. But far less is known about this peak in the infrared. And so one of our key goals is to learn about the galaxies which dominate the cosmic infrared background. It's important to take, a look at what I mean by dust-obscured starbursts. If you go to very high star formation rates in individual systems, the vast majority of the star formation in that system, if we want to observe it, is actually being absorbed. It's initially emitted in the rest-frame UV. That emission is absorbed by dust and re-radiated in the far infrared. So this is the fraction which is obscured relative to the total SFR. And so that increases substantially. So you're basically seeing almost nothing leak out at very high star formation rates. So this obviously has implications. If you want to understand anything about the evolution of massive galaxies, you have to take a close look at dust obscuration. A typical L-star galaxy at redshift 2 will have only 15 to 20% of its emission coming out in the rest-frame ultraviolet as unobscured, and the remainder, 80%, will be emitted in the far infrared. So today I want to split the talk up into three parts. First, addressing the importance of these dusty galaxies as a probe for galaxy evolution by discussing key sub-millimeter extragalactic survey results. Second, I'll discuss the characteristics of dusty starbursts in relation to normal galaxies, normal being in quotes because what becomes normal in the early universe might be substantially different from what we see around us. And last, I'll discuss DSFGs, dusty star-forming galaxies, as useful environmental beacons in the early universe to very massive structures, some of the largest structures that we know. So discussing some of the background and the importance of dusty starbursts, it's important to rewind a couple decades to the 80s when we had the fantastic data set coming out of IRAS in the early 80s, and then the analysis of these sources. Many nearby luminous infrared galaxies were classified, and it became rather obvious that their evolution could be described as a merging event between two gas-rich disk galaxies that collide, ignite a very heavy episode of star formation through their gas compression. Perhaps you have a buildup of a supermassive black hole, which is accreting its field and is perhaps obscured, then becomes unobscured as the quasar, and then you eventually settle into a massive early-type elliptical galaxy. And this is a schematic of the star formation rate against cosmic time, and you can see that this peak happens when the two systems coalesce. So you can really see a short-lived peak describing these ultraluminous infrared galaxies. But recently there's been another evolutionary picture painted for dusty star-forming galaxies at high redshift. And that's based on this idea that the intergalactic medium was potentially much more dense at early times and had efficient mechanisms to feed gas onto galaxies directly. And for that, you need the gas to be cold and compressed efficiently to fuel high star formation rates without mergers. So this is a secular process by which galaxies are forming their stars. And there is some evidence for this as well, observationally, that at redshift 0, we see very low gas fractions in galaxies, less than 10%. And that's your gas fraction is your star forming fuel. But as you look back at higher redshifts, redshift 1, redshift 2, you see much more significant gas fractions, which could actually fuel very high star formation rates. So there's this dichotomy of evolutionary scenarios describing these high star-forming galaxies, major mergers or secular evolution. But the question still remains if there's a very clear procedure by which you can, it's not clear whether or not you can form galaxies that have individual star formation rates greater than 200 solar mass per year without merging. And it would be very nice, of course, to find concrete evidence of these cold flows and secular processes. So, to give a little context, I'll describe some results from the submillimeter surveys. The key advantage of submillimeter is that it has a very negative K correction. And what I mean by that is illustrated with this movie. I haven't started it yet, but it illustrates a typical spectral energy distribution of a dusty galaxy. And it has a fixed luminosity, and I push it back in redshift. And the submillimeter regime is represented by this yellow area, specifically 850 micron, this yellow bar. So as I push this fixed luminosity system back in redshift, of course, the flux density, observed flux density drops, but over a large range of epochs, it's actually rather stable because of the significant slope on the Rayleigh-Jeans scale of the black body. So this very negative submillimeter K correction means that if there are redshift 4, 6, 8 dusty starbursts out there, the submillimeter will detect them. Of course, gathering the redshift information is another ballpark altogether, but this is really extraordinary in that it means we don't have to build much, much larger facilities to detect these systems. If they're out there, we can use the existing facilities modulo the confusion noise. So I showed this at the beginning of the talk, but just to kind of give you the sense of scale, this is 850 micron millimeter map from SCUBA against the optical mosaic of the whole deep field. And the thing that you'll really take note of course, is the confusion noise and how the beam is so poor at some millimeter wavelengths with respect to the optical. So what that means is it's very hard to learn anything in great detail about individual sources. For example, the brightest source in this map is called 850.1, and that source took 15 years to get a redshift confirmation for. And of course, that was obtained by Phoebe and Walter at MPIA fairly recently in 2012 at a redshift of 5.2. And what you'll notice is this is an optical image in the background. It has absolutely no counterpart whatsoever. It's completely obscured, but it has been confirmed by a variety of CO transitions in C+. And this is really useful, and the nominal, surefire way of getting a redshift for some millimeter galaxies, but it's observationally expensive, even in the age where we have wide bandwidth receivers at millimeter wavelengths on facilities like Noema and Alma. So the traditional technique was to get around this by targeting these sources, getting positions via radio continuum maps, where you have precise positions and there's a correlation between far infrared and radio emission in all star-forming galaxies. And using that radio position, you can then precisely target optical counterparts and try to get optical spectral identifications, which is more efficient for large samples. And this is what was done over the past decade, particularly Scott Chapman's work in 2005 summarizing the redshift distribution of submillimeter galaxies. So from all of this decades of work, a couple of key conclusions came to light. What we know about dusty star-forming galaxies, this is circa 2007 based on samples of 5 to 75 galaxies. So it's not an enormous sample that we're working with, but it has been rather up to date, even as of yet, in terms of some of the physical conclusions. So what we've determined is that their redshift distribution peaks at around redshift 2.5. Their star formation rates can be typically several hundred solar masses per year. They contribute at least 10% to the cosmic star formation rate density at redshift greater than 2, although this calculation is highly dependent on how complete your samples are. Their rust frame UV optical spectra underestimate the star formation rates by factors of 100. So there's a huge disconnect between the two regimes. They're some of the most massive galaxies at their epoch. Most are pure starbursts, and there was originally a theory that maybe they were just dominated by AGN, and that was driving their far infrared luminosity, but that's been shown to be largely not the case. And most submillimeter galaxies have been shown through more beautiful kinematic data from mostly CO observations that they're triggered by major mergers. So that picture is rather conclusive and consistent with what we find in the local universe. But that's not the end of the story. So as of around 2007, when this data, when all of these conclusions had come to light, this was the landscape of submillimeter extragalactic surveys in terms of survey area against luminosity limit. You can find this plot in our recent review paper in Physics Report. Most surveys were sensitive to a few hundred solar masses per year. That's a few times 10 to the 12 solar luminosities. But they were relatively small, less than a degree in scale. And that's changed dramatically over the past 5 years, really. And we have a variety of new surveys, some very wide and shallow surveys from the South Pole Telescope and the Atomic Cosmology Telescope, some ultra-deep small beam size surveys from Scuba 2 and the Aztec instrument coming on the LMT, and some wide and medium depth surveys from Herschel Space Observatory.
So those initial sets of points were confusion limited?
Yeah. They're all confusion limited. So the confusion limit for these facilities at 850 microns was 0.7 milliginskys. It's pretty typical, and that corresponds at redshift 2.5 to these luminosities.
And so Scuba 2 gets lower because it's got a smaller.
It's smaller. Yeah. So the point size here is proportional to the beam size. So just to briefly summarize some of the results from Herschel that I was working on over as a postdoc in Hawaii for a few years, I targeted spectroscopically over 1,600 of these dusty star-forming galaxies. And the advantage here is because we have wide area coverage from Herschel, I was able to target these rather efficiently, whereas before we just didn't have the samples because we had very small area surveys. So this is just showing you a sample of some of the spectra going from very low redshift to high redshift. A key result of this is that photometric redshifts, this was somewhat known beforehand, but it's good to verify that photometric redshifts for dusty galaxies are quite unreliable, by a factor of 5 or so more than you see for typical UV-selective galaxies. And we were able to increase the number of spectroscopically confirmed dusty galaxies by over tenfold. This purple distribution down here is the original Chapman 2005 work, and what we have here is the spectroscopic sample from the work on Herschel galaxies. So what has this implied for the history of cosmic star formation from the infrared? Here I show a plot, again rewinding the clock to 2006. All of the pink points in the background are optical UV estimates corrected for extinction. So theoretically this is the total, including all of the dust. And here I show the few estimates we had from dust-only surveys. At 24 micron from Spitzer, which became rest 12 microns at high redshift, and then 850 microns from Scuba. And the unfortunate thing with these data sets at that point is that 24 microns is not a direct probe of your far infrared emission. It's not tracing star formation perfectly well. And 850 microns is much better. It's tracing your far infrared black body, but it's dramatically incomplete because it's very difficult to get redshifts for these systems. So in 2015, we filled this in dramatically, thanks to, in large part, Herschel and some of these more recent submillimeter surveys that attempt to be much more complete. And what we find is out to redshift 2 of the past 2, we have a good estimate of dust contribution to the star formation rate landscape. But we have a lot of work to do at higher redshifts, and mainly that's involved with getting accurate redshifts for these systems, which is harder than it sounds. And then we have to ask the question, okay, well now that we have an accurate census, how many of them are mergers and how many of them are secularly accreting? And that answer is not very clear. We have several works from samples of 75 unresolved CO detections, around 20 which are resolved, and then we have another 20 or so dusty starbursts detected in H alpha. And these kinematic samples are really key to understanding whether or not you have a merger. And in some cases, it's very clearly a train wreck, whereas in other cases, it looks like a smoothly rotating work by Hung, which recently came out this year, what she did is she took local ultraluminous infrared galaxies, which are all train wreck mergers, and she artificially redshifted their H alpha data cubes to redshift 1.5 and asked whether or not you would be able to classify it as a merger still at that high redshift. And unfortunately, in some cases, you see profiles which are consistent with smoothly rotating disks. So we need to really be careful in our evolutionary conclusions with regards to kinematic maps at high redshift. But so to take a step back from our submillimeter deep field continuum surveys, we have a few outstanding questions. One is how common it is that how common are the most extreme starbursts, particularly at the highest redshifts? And does observational multiplicity cloud our interpretation of what high star formation rates are physically plausible? What I mean by that is here I'm showing a particular source which was detected as a single submillimeter source in the Leboka map of the CDS South, which has been followed up with ALMA interferometrically, and it reveals that actually that one source is not one, but it's 3 independent sources. And it's unclear whether or not those 3 sources sit at the same redshift. And if they don't sit at the same redshift, then perhaps instead of a 1,000 solar mass per year galaxy, you have 3, few hundred solar mass per year galaxies. That our interpretation of and the theoretical difficulty in modeling 1,000 solar mass per year galaxies has just been made quite a bit easier. So this is an unsolved picture just due to the very difficult aspects of following these sources up. And another key frontier is asking how many of these sources sit at the earliest epochs, at redshift greater than 5. There are a handful of them known between redshift 5 and 6.4, but they've been found in rather serendipitous fashions, and so we don't have a very good estimate of how many of them sit at these earliest epochs. But they are incredibly massive and very violent, so it is a rather interesting case to constrain theoretical models. So I want to transition now to the second element in characterizing these dusty starbursts in relation to normal galaxies in terms of their UV color. So the backbone of what we think of extinction defined as is, if we look at a region that's relatively unobscured, we see rather blue colors. If there's lots of star formation happening in that region, lots of UV emission, and if it's dust obscured, it's redder by nature, and that's due to preferential attenuation of bluer light. And follow-on to this is that the logical step is that galaxies with more dust are probably very red. And this has formed the backbone of some galaxy selection techniques at high redshift. Here I just showed the dog selection, which is comparing a color R minus 24 microns, and it's selecting the reddest of those systems and calling them dust-obscured galaxies. So the contrapositive statement is also probably correct if we accept the first statement, that blue galaxies are probably not that dusty. And this has been used time and again in the literature as well. For example, this work by Richard Bowens in 2009, and even more recent papers as well, showing that line and break galaxies are potentially progressively bluer at higher and higher redshifts. And what that implies here is a plot of the relative dustiness of the universe at early epochs. They determined that there's just less dust at early epochs, which, might be correct to a point, but it's totally determined by this fact of an analysis of the rest frame UV colors being blue. And the backbone of this framework is the IRX beta relationship. So IRX is the ratio of IR luminosity to UV luminosity, or the relative dustiness, and in comparison to the rest frame UV slope beta. So that's how blue or red your galaxy spectrum is. And this was calibrated empirically back in 1999 by Mirror et al. For a sample of blue compact nearby starbursts. And it's been confirmed relatively recently with a sample of redshift 2 lemon break galaxies as well. But the important thing about this is, in the search for the highest redshift galaxies and characterizing them, what is often used, this relationship is often used so that if you observe a distribution in rest frame UV slope beta, then you infer a distribution of IRX values or dustiness. And the bluer that distribution is, the less dusty it is. But the exception to all of this is where dusty star-forming galaxies sit. They sit well above the relationship in this region where they're relatively blue, yet quite dusty. So this is why UV estimates to the star formation rate of these types of dusty systems is so poor and underestimates the total by factors of 100 or so. So what we did recently is we wanted to quantify this a bit more. It's been known for a while that dusty galaxies are bluer or dustier than expected by IRX beta. But we thought it would be valuable to look at this with good statistics. So this is the actual data. Here we have kind of a recent calibration of the IRX beta relationship. And this cloud in the background are all dusty star-forming galaxies in the cosmos field. So a sample of 4,000 systems between redshift 0 and 3.5. And we wanted to figure out what was driving, which systems sat on the relationship and which systems sat substantially above the relationship. So we did that with this quantity delta beta, which is basically measuring the deviation from IRX beta, where negative delta beta is blue and positive is red. And what we found is that the correlation fits best with infrared luminosity or star formation rate. So as you increase the star formation rate in galaxies, you get to a point where then you break off of the relation at around 50 solar masses per year. And this happens not only in local systems, but it seems to happen at roughly the same luminosity at high redshift as well.
Beta is the observed SCD or the intrinsic SCD?
Sorry?
Is beta dust corrected or is it the observed
No,
SCD or
it's
the
the
intrinsic?
observed. So the interesting thing too is that the break appears to have roughly the same dependence on luminosity. So not only are dusty galaxies bluer than expected, they're bluer by a certain amount proportional to their star formation rate. So dusty galaxies above 10 to the 11.5 or 50 solar masses per year are bluer than expected. And the obvious explanation for this is geometry. And this has been around for a while. Here I just showed an example from Chapman in 2004 showing the infrared emission in dust-obscured starbursts, which is resolved with interferometers, and the UV emission here in black is often offset substantially into two distinct knots. And if you think about it in a simplified picture where you have two distinct knots, one, they both sit on the relationship. A is the very dusty component, B is the very UV luminous component. If you can't resolve the system, then the result that you observe will sit well above the relationship. But if those two components are not so dramatically different from one another, your result is not so substantially above the relationship. So to get something well above, you need actually a dichotomy within the system of very dust-obscured regions and very unobscured regions. So if we make a cartoon of this dustiness, I or X value, we see if you have two distinct regions that are substantially separated, then that can mirror what we're actually observing. And what this means, so one might think naively that if the process dominating the evolution of dusty galaxies of high redshift is dramatically different from the local universe, in other words, these are secular disks, that you might expect something that's constant, that you don't have the same level of variation of dustiness or patchiness throughout the system. But this is what we actually see, and this implies that patchy geometries really dominate these systems, and that's an important factor which is actually proportional to the infrared luminosity, no matter what redshift you set up. So last, I want to discuss briefly dusty star-forming galaxies as useful environmental beacons to the early universe. So what do I mean by this? If we want to look for some of the most massive substructures in the universe, in the nearby redshift 0 universe, we look for virialized clusters. They often have hot intercluster medium, which has been heated. It emits X-rays. It also absorbs CMB photons by the Siemens-Zoltovich effect. There are often massive galaxies, plenty of massive galaxies in clusters. Might have a massive brightest cluster galaxy at the center, and also have a red sequence, so the galaxy might be quenched relative to galaxies in the field. But if we look at earlier epochs, redshift greater than 2, and we want to understand how these clusters form, then we're looking at a different picture altogether. The structures will be much physically larger, and the gas will not be so heated, and there might not be a red sequence because the galaxies are not yet at the point where they're substantially evolved. Here I'm highlighting a plot from Jose Oñor's 2014 paper, which illustrates the relative volume occupied by a halo over time. So redshift 0, you have a very compact structure, and at redshift 2, you have something that is several hundred times larger. So a typical protocluster would be 20 megaparsecs on its side at redshift 2. And that changes the game substantially in terms of looking for these things observationally. You can find them through Lyman-Gray galaxies, spectroscopic conformation, and this has been done in Chuck Seidel's work quite a bit, but it requires a lot of observing time and a lot of spectroscopic conformations. Another technique is wide-field narrowband surveys around H alpha or Lyman alpha, and those can be very efficient, but of course you might suffer from underestimating relative levels of dust obscuration, or you might be sensitive to interlopers at various levels. Another technique, which has been out there but not really utilized entirely to its maximum capability, is using rare galaxies, or dusty star-forming galaxies, and the combination with luminous AGN or quasars to probe these massive structures. And just to give you an idea, of course, the huge advantage of using these rare galaxies is the difference in their volume density. So if you take this typical protocluster of a rather marginal, because you would actually expect a large number of systems in that type of volume intrinsically in the field. And you also need to be rather spectroscopically complete, rather. But dusty star-forming galaxies in AGN are much more rare, so that in this typical volume in the field, you only expect 0.3 systems, as opposed to 25 lemon break galaxies. So any overdensity that you measure will be significant and very easy to pick out. There has been a discussion of whether or not this is actually a useful technique. There's this recent paper by Miller et al. Discussing that perhaps the bias in the submillimeter galaxy population is false, and that they are poor tracers of massive clusters. And that's based on the argument that they are Poisson limited. In other words, there are so few SMGs that if you happen to pick up 2 or 3 in one volume, that doesn't necessarily mean that you're tracing a massive overdensity due to the noise. But you see here, these are lemon break galaxies. The bias with mass overdensity, galaxy overdensity, and similar galaxies are rather uncorrelated. But that's not the end of the story. If you look closer at this work, what you see is as you increase the number of submillimeter galaxies you're detecting, past a threshold of 5 or 6, you are consistently probing the most massive structures. So as long as you pass some threshold of detecting at least 5 or 6 within one relative volume, then you might be pretty successful in identifying these structures. So there have been SMG-rich protoclusters at high redshift. There's this redshift 2 structure with 8 to 9 SMGs and 25 lemon break galaxies, summarized in Chapman et al. 2009. And it mirrors rather well what we expect from simulations in terms of the filamentary nature and spatial distribution of systems. And recently we found another parallel structure at redshift 2.5, which has 7 submillimeter galaxies and 9 AGN. One is an obvious QSO, and another is a very radio-loud source. So this is particularly interesting because it's very spread out and would have been very difficult to identify in lemon break galaxy overdensities alone. Another interesting add-on to this is, given the number of SMGs and QSOs we're detecting in this structure, those types of galaxies are intrinsically thought to be very short-lived. They might last, 190 years. And if you're observing so many of these systems at the same time, the probability that they're all they happen to go on at once, if they're unrelated, is very, very low. It's less than, 0.1%. So if they do intrinsically have these short time scales, it means the structure should not exist unless they were triggered simultaneously, which is interesting because here this might be evidence that you have a triggering mechanism happening over a 4,000, 5,000 megaparsec cube volume, which would be rather extraordinary. But on the other hand, you can view it as an argument that maybe those events aren't as short-lived as we might normally think. If the SMGs have giga-year timescales, then it becomes much more plausible, and these structures should exist everywhere. So this is one thing that we really need to try to pin down, what the cluster star formation properties look like over cosmic time, whether or not they mirror the galaxy properties in having a short burst and then quenching episode, or if they have a period of long, extended, heightened star formation followed by quenching at later times.
This duty cycle comes from clustering? How do you know the duty cycle?
No, the duty cycle comes from gas depletion timescale measurements of the population as a whole. We don't have the gas measurements for these systems. So that's actually the next step, is observing these systems and see over.
If I replenish the gas somehow.
Yeah, exactly. Yeah, that's perfectly plausible, and that can be environmentally.
I mean, there's another way to get duty cycle, which is to just measure the clustering, and then just compare the number density of SMGs to the number density of our halos. With that balance.
Provided, I mean, ideally, I think it's nice if we try to constrain this completely observationally, but yeah, that would be another way to get around it. So the next step that we really want is to get CO molecular gas observations, to get a kinematic profile, and understand our gas mass in each of these systems, compare them to the star formation rate, and get gas depletion timescales. So in summary, I'll just briefly go over the three areas. It's the first part of the talk, I discussed taking census of dust-obscured starbursts and via these submillimeter surveys. And while we've made great strides in surveying and becoming more complete with our submillimeter surveys and understanding the role of dust obscuration at early times, we don't yet have very good constraints on what triggers these systems, whether or not they are mergers or not. And second, I discussed their colors, and dusty galaxies seem to be much bluer than you would expect due to patchy geometries. This isn't a particularly new revelation, but I think it's rather remarkable that you've seen the exact same behavior at high redshift that we see at redshift 0. And last, I think it will be a rather useful technique at, in the next several years as we become better at spectroscopically confirming these forces over large areas. We can use rare galaxies like DSMGs and the AGN as useful, effective observational probes of massive overdensities. Thank you.
What you call star formation rate is in fact carbon per rate total luminosity, right?
Effectively for these systems, yeah, that's going to be the total. It's 95 to 99% of the total.
Assuming a star, the mass distribution of the stars like in the rich universe.
Yeah. I mean, we're applying, Chavrier IMF and kind of assumptions that are calibrated locally, of course.
So how about these Z equals 6 or 7 having a lot of population 0 stars?
Right.
Of 500 solar masses and no missions.
Yeah.
That is in particular important if you have this gas informal scenario. Then it might be quite different.
Yeah, it could very well be. I mean, I think, observationally we're pretty far from putting good constraints on this. Just the samples themselves are so limited, much less detailed analysis of the physics.
So then you would need less gas, for instance, to get
Yeah.
the luminosity. Or the
Right,
same kind of
right,
stuff.
because you're producing more high mass stars.
Good, thanks.
For the dusty galaxies are bluer.
Yeah.
I understood your argument that if you have this unresolved population, that you end up being off that calibration curve. But doesn't that imply that if you did dust correct, the intrinsic SED is actually then super blue? How blue are you relative to just regular galaxies? If you were to
You're not
extinction?
much bluer than, you're not bluer than blue LBGs.
Okay.
You're
bluer than you should be.
bluer than you should be, because you not know, if over 99% of the emission in this system is coming out of the infrared, then this is probably pretty red, right? But that's not what we're seeing. We're seeing that basically they masquerade as low luminosity, greenish galaxies.
I had a question about this puzzle or the duty cycle. So, from the number of massive galaxies that we have in the local universe,
Yeah.
isn't there a limit on how long you can form 100 solar masses per year? Wouldn't you predict too many massive galaxies if you would do
Yeah,
this?
yeah. I mean, there's a constraint from that as well, right? I mean, so that kind of supports the fact that you're not able to sustain super high star formation rates for maybe a year or more.
So where is that limit currently? I mean, I would say 100 million years already sounds like quite a lot to me.
Oh, well, yeah, that's observationally what we see from depletion timescales. Is, 100 megayears is pretty typical, and that's independent of doing that comparison to the number of massive galaxies nearby. I haven't done that directly.
And I have a question about the second statement there. I mean, so I think it's related to the previous question. So if I just think of one clump which is very obscure, and something else of the galaxy that comes out, and the clump that is obscured, you simply don't see it in the universe.
Yeah.
So what is the exact statement to say that there's no change?
Oh,
Does it mean that you see the same clump to the rest of the galaxy?
No, so what we see, by no change, I mean locally at redshift 0, all of the systems that are this luminous appear to be very patchy in that you, globally, the majority of the system is dust obscured, but you see little patches of UV light leaking out here and there, which dominates the UV color, and the rest of it is dominated.
But so is the statement
That is the same at redshift 0 and redshift 3.5.
but so it's not a quantitative statement, it's just saying that there's something very obscure and something that you see.
Yeah,
It doesn't say that
exactly.
the galaxies look
But
the same.
a necessity of this is that distribution of dustiness has to be somewhat bimodal. It can't be an even distribution, because if it were an even distribution, then you would sit on the IRS beta relationship. So to get that significant deviation, you just need a bimodal distribution in A sub B, or in your obscuration.
Okay, but it doesn't say anything about how much is obscured compared to. I mean, it does mean something is able to come out and the rest is obscured, and the rest is actually the dominant part.
Yeah, the rest is the dominant part. So if the rest is not as significant, then you're not going to be as far off the relation. So the deviation scales with that extreme biomodality.
Since you now have a quite considerable sample of such objects and observations, is there any evidence on changes of the dust properties themselves with such shifting?
Oh yeah, that's a very good question. That has not been looked at in detail in this type of system. It's just now getting to the point where we can look at, the attenuation properties of dust and UV and redshift 2 samples, but those are predominantly going to be these optically selective sources. It hasn't gotten quite to that point yet. I think we've just been building samples, and so we have some work to do.
So how would one characterize, if in the future you'd like to characterize the dust properties of 20 redshift, how would you do it?
Oh yeah, well, I mean, there are a few different ways. I mean, what you want to understand is your attenuation curve, right, in these systems, and whether or not you're following some Calzetti extinction